Cryptic repeating fast radio bursts, FRBs, traced to cosmic blasts, fuel speculations about alien technology. And we're going to have a video by NASA on what these fast radio bursts are. They're finding more and more all the time from our galaxy and other galaxies. Fast radio bursts, or FRBs, are a type of transient radio pulse. They were first discovered recently in 2007. Astronomers regularly detect the cosmic phenomena, which is often tracked back to galaxies which are billions of light years away from us, but are yet to determine the actual cause of these flashes. They don't know why they take place. A mysterious repeating fast radio burst has been discovered as the cause of a set of cosmic explosions called FRB 121102, the largest set of fast radio bursts, or FRB, events registered up to now, and it was detected by researchers during testing of China's 500-meter aperture spherical radio telescope, or FAST for short, and it was being commissioned. Over a period of 47 days between August 29 and October 29, 2019, the team of US and Chinese scientists detected 1,652 millisecond-long emissions of radio waves in space. In their study published in journal Nature, the team they stated their hope that the discovery of this activity from FRB 121102, known as a repeating fast radio burst since 2016, would help scientists learn more about the potential source of these fast radio bursts. This was the first time that one FRB source was studied in such great detail, they said. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. They said the large burst set helped our team hone in like never before on the characteristic energy distribution of FRBs, which sheds new light on the engine that powers these mysterious phenomena. Astrophysicist Bing Zhang, professor, University of Nevada, Los Angeles, said, and he was the study co-author. The energy of the signals registered in the latest study severely constrains the possibility that FRB 121102 comes from an isolated compact object, the study co-author Wang Pei said. He's assistant professor from the National Astronomical Observations of Chinese Academy of Sciences. In a statement, he said, while solitary radio bursts are not repeated, fast radio bursts like FRB 121102, discovered in 2007, were found to emit brief energetic radio waves multiple times in 2016. Some fast radio bursts capable of discharging more energy than hundreds of millions of suns have previously been traced back to their distant galaxies, and thus FRB 121102 was traced back to its small dwarf galaxy more than 3 billion light years away in 2017. But scientists have yet to determine the exact origin and the cause of these flashes. Why are they taking place? Some people opt for more sensational explanations, suggesting alien technology could be behind these bursts, but evaporating black holes, colliding dense objects, or hypermagnetized neutron stars and magnetars produced when young massive stars explode and die are what scientists theorize could be triggering these FRB outbursts. These dense stars possess the strongest magnetic fields found in the universe. 6 new fast radio bursts, including a repeated one like FRB 121102, have been detected with the Commensal Radio Astronomy Fast Survey. And as the world's largest antenna, FAST's sensitivity proves to be conducive to revealing intricacies of cosmic transients, including FRBs, said professor at National Astronomical Observations of Chinese Academy of Sciences, lead author Li Di. And let's go to one of the NASA videos concerning these fast radio bursts and where they found them, and they still are a mystery.
In April 2020, astronomers detected an unusually bright and powerful radio signal never before recorded in our home galaxy. The source is a magnetar, a type of compact object with the strongest magnetic fields in the cosmos. Like pulsars and neutron stars, magnetars are the crushed cores left behind when a massive star explodes, but their super strong magnetic fields put them in a class by themselves. The fields are up to 1,000 times stronger than typical neutron stars, and over 10 trillion times stronger than a refrigerator magnet. They can rip molecules apart from thousands of miles away, distort the shapes of atoms, and store enormous amounts of energy. On April 27th, the magnetar, named SGR 1935, produced a rapid-fire storm of short, powerful X-ray bursts that lasted hours. The activity, first spotted by Swift, was also monitored by NASA's Fermi Gamma Ray Space Telescope and the NICER X-ray Telescope on the International Space Station, along with other space missions. As the storm wound down early on April 28th, NICER recorded some 200 X-ray bursts in just 20 minutes. Later that day, SGR 1935 fired off another X-ray burst. This time, though, it was accompanied by something new, a powerful pulse of radio waves, lasting 1,000th of a second. CHIME, a radio telescope in British Columbia, led by several Canadian universities, discovered the signal and determined it came from the vicinity of SGR 1935. Another experiment, called STARE-2, and operated by Caltech and NASA's Jet Propulsion Laboratory, saw an even brighter signal at different radio wavelengths. Since 2007, astronomers have been trying to understand the sources of powerful millisecond radio signals called fast radio bursts seen from other galaxies. Magnetars have been prominent suspects. The duration and energy release of SGR 1935's radio signal is closer to fast radio bursts than any other source. For the first time, astronomers saw a magnetar in our own backyard produce a signal only previously seen in other galaxies. The discovery strengthens the case that magnetars are responsible for at least some fast radio bursts. Data from NICER and Fermi on X-ray bursts at the end of the storm showed that they differed from the one that coincided with the radio signal. This event's characteristics set it apart from the other eruptions, and further study may provide clues about how it also powered the radio burst. Radio waves from normal pulsars originate high above their surfaces. Exactly where and how, we don't know. A big eruption could launch a cloud of plasma to high enough that a radio burst could form. Never before have astronomers seen a fast radio burst so close to home. It's just one more reason to watch the skies, and to keep tabs on the strongest magnets in the universe.
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma-ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma-ray bursts that last longer than 2 seconds are the most common, and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's Swift satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes. Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging star's magnetic field organizes itself into outwardly directed components capable of forming a jet. the Marianas supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows 2 neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic strength 1 billion times greater than the Sun's. The simulation shows the same disorderly behavior of the matter and magnetic fields. Both structures gradually become more organized, but what's important here is the white magnetic field. Amidst this incredible turmoil, the white field has taken on the character of a jet, although no matter is flowing through it when the simulation ends. Showing that chaotic magnetic fields suddenly become organized as jets provides scientists with the missing link. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.